And first, we're going to talk about acids. Acids produce hydrogen ions, or when added to water, H3O plus ions. Hydrogen ions are just protons. If you think about it, a hydrogen atom only has an electron and a proton. As an ion, we lose the one electron, and so all we have left is a proton. H3O plus ions are called hydronium ions. Here are some examples of acids. Hydrochloric acid, which is found in your stomach, HCl. Acetic acid, vinegar, found in fruits and vegetables, some types of salad dressing. Citric acid, found in citrus fruits. Notice that in every case that you've been shown here, there is an H in front. And when this is dissolved in water, basically you'll get hydrogen ions, and then you'll get some other type of negative ion. Chlorine ions for the hydrochloric, acetate ions for the acetic acid, and citrate ions for the citric acid. While there's not a lot of examples here, there's also another pattern that you're just getting to see, which is the number of hydrogen ions in the compound will match the charge of the negative ion. So if the negative ion is charge of -1, then you have 1 hydrogen in the compound. Charge is a -3, you have 3 hydrogens, such as in the citric acid one. Properties of an acid. Acid comes from the Latin word acidus, which means sour, such as lemons and limes, the sour taste in those fruits. Acids have a sour taste. Acids conduct electricity because, of course, they split into ions, hydrogen ions and the negative ions, and therefore conduct electricity. Acids corrode metals. Corrode means eats away or destroys the metals, and in the process produces hydrogen gas. And hydrogen is one of the gens, so H2 gas. Also, it's used to corrode carbonates, limestone, marble, concrete, and in the process produces CO2. In fact, we have a discus ring out near the track in which we just poured acid on it last week to, in fact, because it got too smooth, and so rough it out a little bit, we put some acid on it to eat away some of the concrete that makes the ring. Acids, of course, neutralize bases, and they change blue litmus paper to red. We will have a couple of labs in which we will see the color effects of an acid versus a base, some of which you could even do at home with household chemicals. That actually kind of a cool result. Another opportunity for some extra credit in a lab coming up next week. Bases. Bases produce hydroxide ions when dissolved in water. That is the Arrhenius definition. Bases also are hydrogen ion acceptors, which is the Bronsted-Lowry definition. So you'll have to be aware of both definitions on an exam. Acids are easy. They just produce hydrogen ions. But bases, there's a couple of different definitions based on the historical understanding of the way bases works. The original one was the Arrhenius definition. And then Bronsted-Lowry realized that there were some bases or some substances that act as bases that don't actually have OH in them and therefore needed to be included. And so the definition got broadened. Some examples of bases, sodium hydroxide, NaOH, which you can find in soaps, magnesium hydroxide, MgOH2, which can be found in antacids, and then calcium hydroxide, CaOH2, a form of lime, which is a part of whitewash and plasters. And then something that doesn't actually have an OH in it, baking soda, NaHCO3, sodium hydrogen carbonate, and ammonia, NH3. Either one of those actually have OH ions in them. Again, for the ones that have the OH, notice that we have as many OHs, hydroxide ions, as we do the positive charge. So sodium, positive 1 charge, 1 OH. Magnesium, positive 2 charges an ion, 2 OHs. Same for calcium. And generally speaking, columns 1 and 2, the alkali metals, alkaline earth metals, those are the ones most commonly seen with OH. So, bases. Properties of a base called alkaline, which comes from the Arabic word for ashes, alkali. And if you think back to when we were doing the periodic table, the alkali metals, the alkaline earth metals, alkaline earth for these things were often found in the ashes, such as calcium, after a fire. Bases tend to have a bitter taste, feel slippery, think soaps again, and in fact, most household cleaners are bases. Feels slippery, as I said, corrodes fats, oils, waxes. Again, think of cleaning supplies that will clean up after cooking the fats, the oils that might splatter. As I said, used in soaps and cleaners, also conducts electricity just the way the acids do, because we have the ions when they are dissolved in water. Acids neutralize bases, bases neutralize acids, and they change red litmus paper to blue, whereas the acids change the blue to red. So, kind of like two sides of the same coin, acids and bases, each one neutralizes the other. Both corrode, you can be burned by a strong base just as much as you can be burned by a strong acid? They are on either side of being neutral. And of course, neutral is, generally speaking, where we want to be, pretty close to it. Okay, Lewis, acid-base conjugate pairs. These are two substances related by the loss or gain of a single hydrogen ion. And so what you're going to find is when you mix an acid or a base with water, okay, the hydrogen goes somewhere. So for example, HNO3, that would be nitric acid, mix it in water. Note that the hydrogen goes from the nitric acid, joins the water, H3O plus, and then you also have your nitrate ion. So the HNO3 is considered a donor. It produced the hydrogen ion. It's the acid. The NO3 minus is its conjugate base. But we can go the other direction too. We can think in terms of going backwards. The H3O plus, going backwards, got rid of a hydrogen, donated a hydrogen. And so it would be the conjugate acid, and the H2O, which was the acceptor, was the base. So there'll always be two pairs of acid-base conjugate pairs, because on one side, something has to be donating. On the other side, something has to be receiving. So the donating one is considered the acid. The receiving one is considered the base. And then, as I said, you can go backwards in the other direction and therefore have two pairs of these conjugate acid-base pairs. A test question basically would just be pick out the acid-base pair. So, for example, here we would have the HNO3 and the NO3 minus. Okay, salts. Any ionic compound that is formed from the reaction between an acid and a base. In both the acid and base cases earlier, we talked about one neutralizes the other. Well, when you add an acid to a base, you basically get two things. You get a salt and you get water. Notice that in all three examples on the screen, you've got a salt, an ionic compound, NaCl, metal and nonmetal, KCl, metal and nonmetal, calcium phosphate, again, metal and nonmetals, and water. Now, please note, this is not seawater, okay? Seawater actually has a whole bunch of different kinds of salts in it besides just table salt that we are familiar with. This is just some particular salt based on the actual acid and base in the process and water. And so on a quiz or test, keep that in mind. Okay, it'll be a salt and water that is the result of adding an acid and a base together. But we have a name for ionic compounds, and that is salt. You can also kind of see why the early definitions for acids and bases were H and OH, because of course, if you put the two together, the H from the acid and the OH from the base, there's your H2O for water. Okay, pH, and specifically the pH scale. pH, the power of hydrogen, or if you will, how concentrated is the acid or base solution. And we are specifically, just like the unit we just finished, talking about molarity. Okay, in this case, it would be when we talk about a really strong acid, we mean it's got a lot of hydrogen ions in it. And when we talk about a weak acid, we mean that it does not have very many hydrogen ions dissolved in the solution. Now, the pH scale is basically a logarithmic scale. It goes from 0 to 14, in which those numbers reflect the exponent of the concentration. Notice that the 10 to the negative 7 M molarity concentration, well, that tells you that the amount, the concentration of hydrogen ions in what would basically be neutral is 10 to the minus 7 M. So that means 10 to the negative 7 moles per liter. If we have a concentration that's less than that pH-wise, so the small numbers, 0 to 3, 4 to 6, those are the acids. If we have the high numbers pH-wise, in other words, 8 to 11 and 11 to 14, then we have the bases. And then we subdivide it into strong and weak. So the very lowest numbers are the strong acids, 0, 1, 2, 3. 4, 5, 6 are the weak acids. Strong bases, 8, 9, 10, 11. Strong bases, 11 to 14. Now, please note, of course, these are just the whole numbers. So if I said, it was 6.5, that would still be a weak acid because neutral is 7. So any number that's less than 7, 6.5, 5.2, whatever, would be still an acid. Any number above 7, so 7.3 would be a weak base because it's still above the 7. And then you have some examples here of items that could be considered strong acids. Lemon juice, it would be highly concentrated juice, obviously, not like lemonade. And of course, adding water, diluting the acid, making it weaker. Vinegar and milk are weak acids. Folks, anything that we can eat easily has to generally fall into the weak acid, weak base kind of thing. So it is possible to bite a pepper and burn yourself because it is such a strong acid. That's what's burning you. It is literally an acid inside that pepper. Neutral, pure water. Milk of magnesia, example of a weak base. Ammonia, sodium hydroxide for strong bases. Okay, a little bit of extra vocabulary. First off, neutralization, adding an acid to a base to produce salt and water. You make it neutral if you have equal strength acids and bases. If they're not equal strength, you will neutralize part of it, but it won't necessarily be neutral when you're done. A buffer is something that resists changes to pH. Generally, it's made up of both an acid and a base at the same time, so that if you added an acid, the base part would neutralize it and resist the change in pH. Or if you added a base to it, the acid part of it would neutralize the base and again resist the change in pH. We have buffers in our bodies to try to keep the pH of our bodies in a very narrow range. You may have also heard of some medicines that are buffered so that when you take them, they will not upset your stomach, not make it too acidic. So buffers resist changes to pH.